right, welcome everybody to tonight's lecture, A Billion Years of Hudson Valley History. Our speaker tonight is Kim Fendrick. She is an educator and program coordinator at Rockefeller State Park Preserve. She has a background in geosciences, and her interest in mineralogy has led her to work for NASA on the Mars Curiosity rover's chemistry and mineralogy instrument team. Kim has also studied meteorites and comets at the American Museum of Natural History. We are super excited to have her here tonight to talk about the geology of the Hudson River Valley. So Kim, welcome. Thank you so much for joining us. I'm going to turn it over to you.
Thanks, Sarah. Thanks for inviting me to speak and for hosting. And thank you everybody for tuning in. I've been looking forward to this. This is usually a talk that I give on a hike. So this will be my first time delivering the content virtually, which is kind of nice actually, because there are a lot of visual aids which really help to kind of solidify some of these concepts. So it should be fun. I will go ahead and screen share now. Okay, and can you confirm with me, Sarah, that you can see my screen there?
Yes, looks great.
All right. This is a beautiful photo that I took at Rockwood Hall. If you haven't been there yet, I recommend checking it out. That's at Rockefeller State Park Reserve, where I work. And I just wanted to kind of set the stage for this beautiful valley that I'll be speaking about. So we'll kind of kick it off with a quick intro to plate tectonics, a little recap, maybe some new information to people here today. And then we'll get into the nitty-gritty. So today, this part of North America is tectonically inactive, but this was not always the case. Millions of years ago, the Northeast was the site of multiple continental collisions and the rifting of supercontinents. So we'll talk about these repeated episodes of mountain building, sea level changes, and the erosion and deposition of sediment, and how that shaped the Northeast as we know it today. That occurred in these orogenies listed here, and I'll get into what that means exactly later on. We'll then culminate with the discussion of the last glacial period. And this is just a beautiful picture. If you haven't been to Pelham Bay Park, there are some of the most beautiful outcrops in Westchester and in our area. This picture here is the Heartland Schist. So starting with the basics, just so we can cover some of the terminology I'll be using throughout the talk, the layers of the Earth. So the lithosphere, which is the solid outermost layer, includes the upper mantle and the crust. This is going to be the layer that we're speaking of when we're talking about the plate tectonics and how that contributed to the topography here. The asthenosphere is the semi-solid upper layer of the mantle, and it behaves kind of ductily over time, and that's what allows those lithospheric plates overhead to kind of float around and interact with one another. And then you have the mantle. It's a mostly solid silicate rock and comprises 84% of Earth's volume. Then we have the core, which is the spherical innermost layer, and it's made of iron and nickel. The liquid outer core is what contributes to our magnetosphere. So when we talk about plate tectonics, we're talking about the large-scale motion of the plates making up the Earth's lithosphere, or lithosphere meaning the rock layer, right? So the crust. And so the plates consist of both continental and oceanic crust and the uppermost layer of the mantle. The relative movement of these plates ranges from 0 to 4 inches annually. That's about the rate of the growth of your fingernails. And at the boundaries of these plates are where mountains are formed, new rock is created, old rock is destroyed, and things like earthquakes and volcanoes occur. Plate tectonics is driven by convection within the mantle. So, for example, here you have hotter, less dense mantle that rises towards the surface. As it reaches the surface, it may cool and form new crust, and it'll also effectively push those lithospheric plates around and kind of out of its way. The rock that's cooled and is a little bit more dense will be subducted and sort of sucked back down into the mantle, and then begins to heat up again, where it rises and kind of continues this cycle of convection. So that's the underlying force that drives the lithospheric plates. There are a few different ways that continental or oceanic crust or the plates will interact when they either meet or pass by or separate from each other. So you have here divergent plate boundaries. That's where plates are moving away from one another. When this happens on continental rock, you'll create a rift valley. Some magma may well up underneath. You'll have that valley filled with sediment. When that rift occurs in the ocean, magma may well up to the surface and be extruded out through volcanoes or through a slower, kind of more long-term process like the Mid-Atlantic Ridge, for example. And this is where new rock is created. You also have transform boundaries where plates may slide past one another. A classic example of this is the San Andreas Fault in California. And then you have convergent boundaries. These are the boundaries where plates are colliding with one another. It's a little bit more violent. This will result in formation of mountain ranges, which will be associated with high-grade metamorphism, which is just the intense deformation of rocks due to heat and pressure during that collision. So in all of these scenarios, the rock can't just be infinitely pushed up for both plates. So eventually one of those plates will be subducted or will be kind of sucked down into the mantle as the other plate overrides. And so when you have two oceanic plates or ocean rock colliding with one another, they're both very dense, and you'll end up getting subduction here, melting of that subducted slab as it descends into the mantle. And as that melted material heats up and becomes less dense, it rises back to the surface in the form of volcanoes. And you might end up with something like a volcanic island arc, like the Aleutian Islands, for example, off of the coast of Alaska. When you have ocean and continental rock meeting, the continental rock is less dense. It's typically a bit thicker and it's more buoyant. So that rock will ride up over top. You still might get volcanoes where the oceanic rock is subducted and then melted, but those volcanoes will now form on the margin of the continent. And then you have continent-continent convergence, where the two continents smash together and you get a massive mountain range being formed here and metamorphism happening deep inside that mountain range. And a good example of that would be the Himalayas, where India is colliding with Asia. So where does our story begin? That would be with the formation of Rodinia. So Rodinia was a supercontinent that formed between 1 and 1.3 billion years ago. And this happens kind of periodically as the continents drift and eventually sort of clump together to form one giant continent. And so at the time, this was, like I said, about 1 to 1.3 billion years ago, New York was on the margin of Laurentia. Laurentia comprised of present-day North America and Greenland. And this landmass was rotated 90 degrees to its present-day configuration. So New York was now on the southern kind of tip of North America. And we were also just south of the equator at the time. We were also in a dangerous spot because Amazonia, this other continent here to the southeast, was approaching. And Amazonia comprises of present-day South America. So as Amazonia approached, the ocean closed between these two continents, and ultimately they will collide. This collision and this entire process is called the Grenville orogeny. So the word orogeny is just a term for a mountain building event. And you'll hear me say that a lot throughout the presentation. It basically just means when you have a continental plate collision mountains are built, and we just name them for ease of reference. So here you have the Amazonian continent approaching Laurentia from the southeast. New York is caught up right in the middle here, and the ocean is closing between the two. So that oceanic crust is being subducted under the continent of Laurentia. That plate is starting to melt and form an arc of volcanoes along the margin of the Laurentian continent. These volcanoes are erupting. They're contributing volcanic ash into the shallow sea between the two continents. You're also getting this kind of accretionary wedge of material, sediment that's getting scraped up in between the boundary of these two plates. Then that collision proceeds. The ocean continues to close and Amazonia moves closer. You have a variety of different rock types beginning to form here. There are sedimentary rocks off the coast of Amazonia forming from erosion of the Amazonian continent. You have those sedimentary rocks here from the Laurentian continent, also from the volcanic eruptions. And then you have a little bit of the metamorphism of this accretionary wedge as well. So eventually the two collide and result in intense metamorphism of all of these rock types that existed here. So you have essentially metamorphosed continental rock from both Laurentia and Amazonia. He metamorphosed extrusive and intrusive volcanic rock. So extrusive meaning the lava and ash that came out onto the surface. Intrusive meaning any of that magma that would have cooled within the crust. And then you also have the metamorphosis of the sedimentary rocks that were deposited in this shallow sea from the erosion of both continents. So you can see why the bedrock in our area is so complex, specifically the Fordham Gneiss and the Hudson Highlands, which resulted from this. We have this mixture of different rock types that contributed to their origins. And once things get metamorphosed, it just gets a lot more complicated from there. So remnants of these Grenville Mountains stretch from Canada through North America and even down into Mexico and would have rivaled the Himalayas. They were eventually eroded to a flat plain over time. Most of them currently are buried. However, we do have a couple of exposures of Grenvillian aged rocks in the Adirondacks and in the Hudson Highlands. And that's just due to uplift and subsequent erosion. The Fordham Gneiss, just to show you here, Grenville Highlands. So that's this orange province here. And the Fordham Gneiss, which underlies vast area of Westchester, the Bronx, and northern Manhattan, also formed during this event. It's the oldest rock unit in the Manhattan Prong, aged at 1.1 billion years. And it originated from the sediments that predated the Grenville orogeny, which were then deformed deep within that Grenville mountain belt at very high temperatures and pressures. So those might have been sediments that were in that shallow sea or on the continental margin. And that Fordham Gneiss is this brownish layer that you see here. That's underlying, like I said, most of Westchester, coming down into the Bronx and northern Manhattan. So you'll notice here that the river narrows as it passes through the Hudson Highlands. And that's because the rocks here are harder, they're more dense and more resistant to erosion. And you'll see here a little bit of widening just north and definitely a significant widening So that's a rock that it's in through a river, but it's softer, more easily eroded. Those are rocks like shale, for example. And the Hudson Highlands are composed of gneisses and igneous rocks. So remember, these are much harder and they were formed during the Grenville orogeny. Some examples of this would be the rusty red gneisses in Harriman State Park, formed from the metamorphosis of sedimentary rocks of multiple origins. So kind of like I was just mentioning in the last slide, you have a few different depositional environments and depositional origins for these sediments. So here's just kind of a quick example of that metamorphic pathway from a sedimentary rock to a gneiss. And here are some examples of those depositional environments in the collisions. So you have Amazonia here on the left, Laurentia on the right, and essentially the sedimentary rocks that were metamorphosed into the Harriman gneiss were from the volcanic island arc on Laurentia, so not only erosion of the rock itself, but also the ash. And you also have continental rock that's shed off of Amazonia, continental rock from Laurentia, and all of this just having been compacted and deposited in the ocean between them. So you also have another type of gneiss in the highlands, and that's the Storm King gneiss, for example, which comes from granite. Granite is an intrusive igneous rock, and here you have an example of that, where there's magma welling up from underneath. It intrudes this forming mountain range and kind of just gets caught up there. It never gets extruded out onto the surface, but it cools and solidifies in place underground. So you'll end up with larger crystals like this, but with enough heat and pressure, it can also become a gneiss, just like those sedimentary rocks. It's another reason why it becomes complicated to unravel the history of some of these rocks. You really have to look at the chemistry and the mineralogy within those rocks to really tell what they came from. We also have some unmetamorphosed rocks in the region. Those represent some later intrusions of magma that dated from about 1 to 1.1 billion years old, and they are younger than the sedimentary rock younger than the metamorphic rock they intruded into. So it's worth mentioning that when you have this kind of intense deformational event and you have faulting, the rocks on the surface, they're cooler, they're hard, they can behave brittly and fracture. But deep down where these faults and these fractures are occurring, the rock can behave a little bit more ductily and it will actually shear. And in those shear zones, water is able to get in and kind of percolate through the rock. And what that does is it will mobilize certain elements and redistribute them elsewhere, and creating what we call veins. So here's a nice example from Rockefeller State Park. We have a quartz vein on the Goat Trail. This is just a redistribution of silica, but perhaps more importantly or more interestingly, economically speaking, we have iron concentration in this area. So iron ore from the Hudson Highlands contributed to our success in the Revolutionary War, for example. The Great Chains at Fort Montgomery and West Point were built out of this iron, and they helped to prevent the British advance up the river. And of course, this contributed to our ability to really create the city that we live in, and a lot of the economic gain that we've had from this area. I'll take a quick break for questions. I know that was a lot in only a few minutes. Sarah, do you want to see if anybody's dropped any comments in the chat?
Yeah, we don't have any questions yet in the chat, but we can give folks a minute if they have any questions so far. I think it's been super fascinating to see how much the geology affects like the landscape, and also like I had not thought about, of course, it's obvious now that you pointed out, but that the Hudson Highlands, the river narrows there because the rocks are harder and they don't erode as much. Like, sounds fascinating to think about.
It's cool to think about, like you said, the confluence of how the geology affects the human history, right? I mean, that's a big part of why that became like a choke point and such a important area, like as far as military strategy goes. And I know maybe I won't plant the seeds just yet with the public, but that would be a great hike to do as a joint effort. I would love that.
Yeah, I'm sure we could see that on our side, or I know Fort Montgomery and Stony Point Battlefield, both Revolutionary War history on the other side of the river in the Highlands. All right, now we're getting some questions. We've got Mike would like to know what time frame are we talking about for everything you just described?
Everything meaning, okay, so we started off with the formation of Rodinia, which was 1 to 1.3 billion years ago. And then essentially we're still talking about that. So these rocks formed during that Grenville orogeny. So really basically just ranging from 1 to 1.3 billion years.
Great. Okay. Jennifer just has a great little comment. She says, just wow, hello, this is amazing so far. I'm an earth science and environmental science teacher, so I live for this. I have a deep personal interest in local geology too. So great. Glad you could join us, Jennifer. Michael says, what are some locations where the Grenville outcrops can be seen in the Hudson Highlands?
Yeah, good question. Storm King Mountain, Bear Mountain, Harriman State Park. I want to say Anthony's Nose are some of these original rocks as well. Really just that whole strip of the Hudson Highlands, any of the hikes that you can find in that area are going to be these old Grenvillian rocks. So yeah, and I also have a book that I could recommend later on that gives some more detail about that.
Great. We have some folks who are having trouble with some audio, so I'm just going to reply to them in a second. I'll check for any more questions, and then we can continue. Looks like we're good for now. So folks, if you have more questions, you can drop them in the chat as we go. Oh, here's one more. Charlie says, where do the Highlands start and the Palisades end?
So the Palisades are essentially, the Palisades are an intrusion into the Newark Basin, which abuts the Highlands, and they're separated by the Ramapo Fault. So let's see if I can go back. It's not going to show you in this diagram here, but this is the Palisades sill, this lower kind of portion of the green Newark Basin, and the Hudson Highlands are this orange kind of province here. So they're south and to the southeast. Okay. I like to stop for questions. I'm kind of my teaching style is very question and answer. I like to ask the audience to tell me things. So this is a bit of a change of pace for me, but thank you for contributing, everybody.
Yeah, sorry, I just missed replying. Margaret says, are there any places where rocks from Amazonia can be seen? Is the material of Amazonia different from that of Laurentia?
That's a great question. So at this point, they're essentially one and the same because they kind of just got fused. I'm not sure if there are specific examples of rock that we know came wholly from that continent. I think at this point, it's sort of just a mishmash of material, especially because, as I haven't gotten to quite yet, but as we will discuss, there are subsequent orogenies that deform and contribute to the kind of metamorphism of these rocks. So this is just step one. So maybe we should move on then.
Yep.
All right. So given about, let's say, 400 million years or so, around 600 million years ago, we have the breakup of Rodinia. So this is towards the end of the Precambrian. As Rodinia is breaking up, the Iapetus Ocean is forming between Laurentia and Amazonia. And so you have the formation of Gondwana, which comprises present-day South America, Africa, Antarctica, Australia, and India. And present-day New York is now no longer on the edge of the plate, but had become a passive margin within a plate. So similar to what we have today. Laurentia sort of migrated towards the equator, and sea level rose as the Iapetus Ocean widened, flooding vast areas of the continent. This also coincides roughly with the Cambrian explosion. So the abundant shallow seas that covered much of the land and on the continental margins, and also the warmer climate conditions during the time, plus the availability of nutrients from volcanic sediment on the seafloor, This all allowed life to go from single-celled organisms to complex life. And at this time, life begins to diversify, marking a new era in geologic time. During the time of this passive margin, as New York is now hanging out on the interior of a plate, we have extensive erosion of the Grenville Mountains. So millions of years go by, these mountains are breaking down essentially to a flat plain, and it's depositing massive amounts of sediment and also shells from marine organisms. These deposits result in limestone beds of up to 2 miles in thickness in some places. So these limestones, or otherwise carbonate rocks, are found distributed throughout New York. Much of this area was underwater at that time. This leads to the tectonic orogeny. Things were not passive for very long. For some reason, at one point, the continental plates reversed direction. The Iapetus Ocean began to close once again, and crustal material was subducted under the ocean, leading to melting and the formation of the Taconic Island Arc. This is a volcanic island arc offshore. This island arc was advancing towards the eastern margin of the continent, and as you probably guessed, will eventually collide. So sorry for the quality of these diagrams. They just are my favorite in illustrating my next few points. But so we're going to do a quick breakdown of the tectonic orogeny and what that entailed, because this is a very important orogeny to the bedrock foundation of Manhattan Prong. So the compression of these two plates colliding caused the fracturing and uplift of those carbonate rocks that were deposited from the breakdown of the Grenvillian Mountains. They were exposed to erosion, and all that sediment is running off into the continental shelf under the sea here. So the same time as there was uplift of continental crust, you also had the depression of the eastern margin of the continent, forming a deep marine trough. Sand and carbonates are deposited in the shallower waters offshore, and then silty mud and sand was deposited in the deeper water of the trench, along with volcanic ash from the volcanic island arc that was approaching. These resulted in the carbonates, shales, and sandstones that will later become the basement rocks of the Manhattan Prong. So as this collision proceeded, rocks in the trough were thrust westward over the rocks of the shelf, which were then pushed westward again in a series of thrust faults. This created the Taconic Mountains as high as the Rockies, and also contributed to the uplift of the ancestral Appalachian Mountains. And eventually, the volcanic island arc accreted onto the margin of the continent. So, as you can imagine, unraveling this story becomes very complex. You have older rock overlying younger rock in some areas, which is highly unusual. You have extensive metamorphism, and then of course you have this foreign terrain added into the mix. So to focus on the rocks of the Manhattan Prong for a moment, this is where most of us live, in this general area here. Hello to all our visitors from around the country. Thank you for joining. So the Manhattan Prong is composed of the Fordham gneiss. So this is that metamorphosed layer that formed during the Grenvillian orogeny, and was deformed again during this orogeny here by the encroaching Taconic Island arc. So we have the Fordham that's deformed, as well as all of those sedimentary rocks that were deposited offshore. You have the Inwood marble, which originated from the limestones deposited on the shallow margin of this continent. You have the Manhattan Formation, which is composed of schist, gneiss, and amphibolite. The parent rock of that formation would be the sandstones and shales and some volcanic sediments that were deposited on the continental rise in slightly deeper waters. and in that trench. And then you have the Heartland Formation. Its origin is a little bit contested. It's the same age as the Manhattan, but it differs in composition. So some people estimate that this may have originated on the other side of the Taconic volcanic arc. But for simplicity's sake, we have it here in the diagram right next to each other. But essentially, the depositional environment was very similar, where it was deep water, perhaps ocean trench setting, shales, and turbidites, which are basically just rocks of mixed grain size that were deposited resulting from sort of turbulent flow of water, which will happen on the slope of the continental rise. And then you also have volcanic sediments in the Heartland Formation as well. The Walloomsac schist is a younger layer that was deposited on the eroded surface of the Inwood Marble. And exposures of this layer are sparse. They're overlain by the Manhattan due to thrusting, so it's kind of hard to observe it directly. But the parent rock or the origins of those rocks would be shale and Greywacke turbidites. Greywacke is basically just like sandstone. So just to put that all together, I know this looks kind of crazy, but we've got the Fordham gneiss here in brown. I'm sorry to all my colorblind viewers. I'll do my best to just delineate with my mouse. You've got the Manhattan Formation, which is this yellowish layer with the diagonal stripes. You have the Inwood Marble, that is this orange layer that kind of underlies or surrounds the Fordham gneiss. You have the Yonkers gneiss, which is this pink layer. A little bit confusing because they also chose pink for the Palisades sill, which is completely different, but we'll get to that. And it's worth noting here that the Yonkers gneiss, similar to the Pound Ridge gneiss, which is not pictured here, it's a little bit further northeast, both of those are a result of granitic magmas, so magma of a granite type composition, intruding into the Fordham gneiss during the breakup of Rodinia. So that was around 560 million years ago. And those gneisses are much younger than the Fordham gneiss and sort of kind of broke into that layer from below. You also have, worth noting, the Cortland complex just south of Peekskill, also not pictured, but that represents another igneous body of several intrusions of magma into the rocks of the Manhattan Prong. The Cortland complex is dated a little bit younger at 430 million years ago at the end of the Taconic orogeny. So for all my geology nerds out there, there are plenty of really cool rocks to go and see just in this area, and there's a good amount of variety as well. I will also mention here Cameron's Line. This is a fault that delineates the ancient boundary between the Laurentian plate and the plate that contained the Taconic Island arc, with the Heartland schist being this area over here in also yellow kind of vertical stripes. This was sort of considered like exotic terrain that was accreted onto the margin of the continent. So by that basis, yes, maybe it was rock from the other side of the volcanic island arc, perhaps. And I will also, it's kind of a misnomer to call this a line because this suture zone is not really well defined, and it's contested in a lot of places because of the fact that it was really severely warped due to subsequent orogenies, rifting, and all the changes that occurred in this area. And then I just mentioned here Harrison Gneiss. I'm not going to talk too much about that. And then the Newark group, which we'll get to later, and this pink here, that's the Palisades diabase or the Palisades sill that intruded into these Newark rocks. And this is just a nice diagram to kind of show how the underlying bedrock geology affects the sort of topography. And for example, where the river is, you'll notice that that river just carves through the weaker Inwood limestone, whereas the areas of higher relief, Palisades, here in Manhattan, made of the Manhattan schist, and then the Fort of Gneiss. These are all areas of higher relief as they're much harder and more resistant to erosion. The Palisades Sill is this diabasic intrusion. Again, we'll get to later, but this is another igneous rock that's really hard and resistant to erosion. Okay, stopping again briefly, I'll take a couple questions. And please admire this beautiful photo of the Heartland schist. This is a close-up. I had a pencil in here for scale, but I took it out because it didn't look very nice, but it was about the width of this fold. Oh, you can see a fly for scale right here.
Oh, all right. We have a lot of more great questions. That was super fascinating seeing where the river valley is carved through. So Charlie was wondering, are the Haverstraw Mountains like High Tor considered part of the Highlands?
I want to say probably, but I'm not sure. I might have to look at a map. Haverstraw seems like it would be within the Newark Basin, but I'm not too sure.
All right, Nicole says, when walking on the beach or in a forest, my kids have encountered what they refer to as natural clay. How does that form, and is it really clay?
Yeah, I love that. I love that your kids are that perceptive and thinking like that. Yeah, clay is absolutely natural. Clay forms from the breakdown of minerals like feldspars and micas. So that will essentially, it just has to do with the chemistry of the mineral. But yeah, clay is also what's deposited in the deeper ocean due to the fact that they're just small particles, so they're able to be carried out that far. But yeah, clay is absolutely natural.
If you know anything about the history of construction in New York, you know that the Hudson River is abundant, or was abundant, with clay, particularly in the Haverstraw area. Because we had brick making all up and down the Hudson River throughout the 19th and early 20th century. So if you haven't been to the Haverstraw Brick Museum, you could check that out. Yeah, Nicole also asked, how does your understanding of geology affect the way you think about the earthquake we had around here last week? I knew an earthquake question was going to come up.
I have a whole slide about that, so we will get to it. Right, okay, but I will just say that it was exhilarating. That's the third earthquake I've experienced, and obviously they are can be dangerous in other areas of the world, so don't take it lightly. But that being said, I had an adrenaline rush all day from that. So yeah, I'm pretty thrilled by natural phenomena like that.
Susan asks, what makes shale?
Shale is from the breakdown of other rocks. It's rich in clay, actually, breakdown of feldspars. And so it's really just those finer sediments that get deposited in deep ocean waters. And that's from like breakdown of, could be continental rock, it's just sedimentary rock. So it's kind of like essentially a trash can of of particles from the breakdown of all other types of rocks. But yes, it would be composed of those finer particles. Shale is kind of a reference to the grain size.
Nicole asks, can we see Inwood marble at Inwood Hill Park?
I believe so. I would have to, you can check out that geologic map actually. If you look up the lower Hudson bedrock sheet online, you can look at where some of those areas outcrop. And then there are also some field guides that I could share with you. Mergurian did some trips. And actually my former supervisor at the Museum of Natural History, they led some trips for their Masters of Arts in Teaching program. So they had a geology teachers program. So they did some trips in that area. I could share some of those resources that might help point out where you could find these outcrops.
That'd be great. Thanks. Sarah says, what about the composition of different types of rocks results in varying levels of hardness / susceptibility to erosion?
Yeah, good question. So it has to do with the minerals, what they're composed of, and how the rock is cemented. So for example, an igneous rock or a metamorphic rock, they're essentially welded. The crystals are, there's nothing in between the crystals, versus a like I said, they're kind of like welded together or bonded, versus sedimentary rock, they are cemented together. So they're individual separate particles. Those particles could be rounded due to abrasion rolling around in a stream or offshore in the water. And then they kind of just get clumped and stuck and compressed together. And so they aren't as strong and thus not as resistant to weathering. There's also the factor of the individual minerals themselves having different hardnesses. For example, quartz is much stronger and more resistant to weathering than calcite, for example. And calcite is a carbonate mineral like what you would find in limestone. Quartz is a silicate mineral, and that's what things like granite or gneiss are abundant in. So both of those contribute to the hardness of a rock.
Great. And we have one last question from this section. Corinne, and you might be getting to this, Corinne wants to know, when did the Hudson Highlands Fjord form?
Yes, great question. So we will definitely get to that, but that was much later. The last glacial period ranged from about 115,000 years ago to about 11,700 years ago. So at some point during that time, perhaps during the last glacial maximum, I'm not sure exactly where within that range it might fall. There were also multiple phases of glaciation, so it could have even been earlier. But I would say definitely at some point within the Pleistocene or perhaps the late Pleistocene before the end of the Ice Age.
Great. All right, that's it for questions for now.
Thank you. All right. So moving on to our next collision, the Akkadian orogeny. So it started off in the Ordovician period where you had Avalonia, this volcanic island arc that broke off of the coast of Gondwana and merged with Baltica, which is present-day Europe, before eventually colliding with the eastern margin of Laurentia during the Devonian. So it was roughly 425 to 375 million years ago. This created the Euro-American supercontinent and also added some terrain onto North America. So easternmost Canada, eastern Connecticut, eastern Massachusetts, Rhode Island, and coastal Maine are all Avalonian terrains that accreted onto the continent during this collision. It also contributed to further building of the Appalachian Mountains. At this time, or throughout much of the Devonian, New York was submerged under the Helderberg Sea, and thick limestone beds rich in fossils were accumulating until the Avalonian terrain was sutured onto the continent and the sea essentially dried up. The Akkadian orogeny is known in other places in the world as the Caledonian orogeny, Caledonia being the Latin name for Scotland, because this is where it influenced mountain building in the British Isles, Scandinavia, eastern Greenland, and parts of north central Europe. So it was the same collision, but just different names for it in different regions on Earth. And so this is why we find the same rock types and fossils in Northeast America and in some of these locations. So it's almost like a continuous mountain belt here. It's contested whether or not the Akkadian orogeny contributed to any significant deformation of the rocks in our area. However, the erosion of the Akkadian mountains did contribute as they deposited a huge amount of coarse sediment to the west, forming the Catskill Delta, which make up today's Catskill Mountains. And then we have the Alleghenian orogeny. So this took place between the Pennsylvanian and Permian periods, about 325 to 260 million years ago. And this was the largest mountain building event to affect our area since the Grenville orogeny. The Alleghenian Mountains were as tall as the Himalayas, and this was the final stage in formation of the Appalachian Mountain Belt. This also led to the formation of Pangaea. And at the time, Pangaea was surrounded by a global ocean called Panthalassa. So I won't get into too much of the details of the environmental conditions at the time, but there were a lot of changes in climate and in ocean currents naturally, as you might think, and we had vast deposits of coal swamps that we now tap into for our oil reserves today. We then had areas that were huge deserts, and it also kind of made it difficult for marine life as there were less coastal shallow seas for them to live in. It increased competition and reduced the resources available, and also reduced habitat. So it was kind of a tough time for some of the life on Earth. The Alleghanian orogeny also contributed to the east as it basically intensely folded and faulted the sedimentary rock west of the highlands, creating the Valley and Ridge Province that extends into and through Pennsylvania. Then fast forward to about 200 million years ago, and Pangaea begins to break up. So you have a fracture that opens up between what is now two continents, Laurasia and Gondwana, with the early Atlantic Ocean opening between them. So you have here a reconstruction of what some of those stages might have looked like, going from Pangaea to then Laurasia and Gondwana, and then the further drifting of the continents until they eventually settle into their present-day locations. I won't say settle because they're still moving and they will continue to move. There's some pretty cool reconstructions on YouTube if you want to look up projections for what we think might happen over the next 200 million years. But yeah, it's interesting to think about. So also worth noting, the dinosaurs roamed all of the continents, basically until their extinction at the end of the Cretaceous, so about 65 million years ago. And that was due to what we believe was an asteroid impact in the Yucatan Peninsula. Unfortunately, 3/4 of all species on Earth perished, and that marked an end to the Mesozoic era, end of the Cretaceous, and the beginning of the Cenozoic. Cenozoic meaning new life, Mesozoic meaning middle life, and then Paleo was ancient life because Paleo is where it began. So this leads to rifting. So as these continents are spreading apart and drifting from one another, you have rifting, which is basically fracturing of the continental crust. And it also leads to kind of the stretching and thinning of the deeper crust. So at depth, rocks can behave sort of plastically, whereas at the surface, you have these brittle faults occurring in the surface rock. And so where full rifting occurred, you have the opening of the Atlantic Ocean. Where you only have partial rifting occurring, basins form. You have thinned crust and drop down blocks of rock, and that creates voids that are then filled with sediment. And the Newark Basin is one of these failed rifts. You can kind of think of these basins as like stretch marks on the Earth's crust. So what also tends to happen in these areas is because you have thinner crust here, it relieves pressure on the mantle below, which allows magma to well up to the surface and essentially inject itself between the horizontal layers of sedimentary rock. The Palisades Sill is one of these such intrusions. It has since been exposed due to erosion. So we have here just a quick diagram of that. And you've got the Ramapo Highlands, which is part of the Highlands province here. The Ramapo Fault, keep that one in mind. We'll come back to that. And then you have a few different lava flows that are all associated with those injections of magma into the sedimentary rocks within the Newark Basin. So again, highlighted here, the Newark Basin, just west of the Hudson River. You have our Palisades Sill, and then this non-conformable boundary between these sedimentary rocks and the metamorphosed rocks of the Manhattan Prong basement. And it's worth noting here, this Ramapo Fault is where those initial kind of downdropped blocks slid and were displaced. And it can also be the site of seismic activity. The Palisades sill is a diabase, which is the same composition as basalt or ocean rock, but it's intrusive, so cooled underground, which means it's got slightly larger crystals. Radiometric dating ages this intrusion at about 190 million years ago, and it's got these characteristic columnar joints. So essentially these vertical fractures that you're seeing pictured here, and those formed as the rock cooled and contracted underground. So that can only really happen when it cools a little bit slowly. We also know through geochemical analyses that it formed from 2 or more separate injections of magma. And as you may have seen in person, but just to put in perspective, those exposed cliffs are up to 540 feet in height. And this sill dips to the west, and it kind of dips down underground. At its thickest, it's estimated to be at almost 1,000 feet. All right, so getting to our earthquake discussion, it was funny because I added this slide. I was kind of going over the PowerPoint last week, and I was like, oh, I should mention the fault and earthquakes, and I added this slide like 2 days before the earthquake, or maybe the day before, and the next day I was like, oh my god, I jinxed it. But it was crazy, and so it was really exciting because things like this don't actually happen that often, as far as these magnitude 4 and above. The earthquakes are a characteristic of these rift valleys. You'll get shallow crustal earthquakes, but they're usually not very destructive. Most of them are magnitude 2 or less, and they're not normally felt. So our magnitude 4.8 last week was definitely a bit special. The last 3 eruptions that are of note in recent history would be first 140 years ago as a 5.2 magnitude in New York City in 1884. And then we had magnitude 5.3 in New Jersey, 1783. So that was 286 years ago. And then a 5.2 magnitude in New York in 1737. So they are pretty few and far between, these more significant quakes. And that's because really less than 10% of earthquakes occur with boundaries. So like a lot of us would think of like the Ring of Fire around the Pacific, where you've got all these plate boundaries, volcanoes, lots of really significant earthquakes. Here, intraplate quakes are pretty quiet and much fewer. So that was definitely an exciting experience. We have traced its origin to the Ramapo Fault. It occurred at a depth of about 2.9 miles. And worth noting that the length of this fault is about 185 miles. So it really kind of spans across Pennsylvania through New Jersey and into New York. All right. Oh, also worth mentioning. While they may be a little bit less significant as in terms of their magnitude, the earthquakes in our area, so on the East Coast, tend to be felt at far greater distances than those on the West Coast, and that's because the basement rock here is harder and more dense. So they transmit energy or seismic waves more efficiently than the rocks out west. All right, so just to do a quick recap of everything I just talked about, we'll just kind of jump through it step by step. We had the initial Grenville orogeny 1 billion years ago, which formed the Fordham Gneiss and Hudson Highlands, some of the Adirondacks. So some of these really old rocks that still exist in our area. Then we have rifting as Rodinia breaks apart. Then a while later, we have the initiation of the Taconic orogeny as the Taconic volcanic island arc forms off the coast due to subduction and melting. That island arc proceeds to collide with the eastern margin of the continent and accretes onto the edge of the continent. Then we have Avalonia, another island arc that advances and collides with the continent, also accreting onto our margin. And then we have the collision with Gondwana, Africa here being, that was the portion of Gondwana that collided with us today, or well then, but so present day Africa. So we have the big collision here, formation of Pangaea, everything's all crunched together. And then eventually the rifting and breakup of Pangaea, formation of all of these faults, the Newark Basin and Valley and Ridge Province, and all of the features that we see here today. I will say also, I think I answered that question earlier incorrectly. You asked where you could see Avalonian terrain, or was it Avalonian? I can't remember. We'll have to come back to that at the end, but let's chat later. All right. Oh, Amazonian terrain, perhaps it was. Amazonia would be found currently still in South America, perhaps. I think it was Amazonian terrain you were asking, not Avalonian.
I just flipped back through and it was Amazonian.
Okay, so yeah, so Amazonian terrain, I was thinking of Avalonian terrain when I answered your question. Amazonian terrain should still exist in South America.
Makes sense.
I will take a few questions here.
I don't know. I think everybody might be questioned out. We don't have any waiting for you in the chat.
All right. I will let that percolate then, and we'll stop again after our next segment. Okay. Thanks, Sarah.
Yep.
All right. So fast forward millions of years to the Pleistocene. So that's way up here. We have now the initiation of an ice age. So that was about 2.5 million years ago up until about 11,700 years ago. So at this time, Earth experienced a series of glacial and interglacial periods with at least 4 major pulses of glaciation. Some actually consider this period, the Quaternary Ice Age, to be ongoing because we still have polar ice sheets. But that would just mean that we're in an interglacial period or a period of warming. So that's technically kind of what defines an ice age, is the persistence of ice caps at the poles. So these cyclical periods of glaciation correspond to changes in Earth's orbital pattern, variation in Earth's climate systems, so like ocean currents, the carbon cycle, and also can be affected by other things such as volcanism and changes in solar radiation, for example. So the last glacial period was about 115,000 to that 11,000 years ago, but the last glacial maximum was 25,000 to 18,000 years ago. So that was kind of the last time we really had significant glacial activity in the area, and its end marked the beginning of the Holocene, which is our current time period. So as you can see here, the Laurentide ice sheet is responsible for carving a lot of the topography in the Hudson Valley as it descended south. And when I say descend, you can kind of picture an ice sheet traveling like honey would on a table. So as you contribute more and more snow to these ice caps, it kind of just mushes out and spreads like laterally in all directions. And ice, while it may be solid, generally speaking, it kind of behaves plastically over time, and it does flow. Also worth mentioning, the ice sheet was about 2,000 feet thick in our area. So kind of crazy to picture that. It's like almost the height of the Empire State Building. So some evidence that we see of glaciation in our area would be striations in the rock, where the glaciers expose the bedrock, basically smoothing the surface but leaving behind parallel scratches or striations. Those striations are typically caused by gravel or pebbles or rocks that the glacier is carrying that are stuck to the bottom of the glacier as they kind of scrape over the surface of bedrock. So these are some things to look out for as you hike in this area. They're pretty ubiquitous. So you'll see striations. You'll also see what are called chatter marks. That's essentially where the glaciers sort of gouged chunks of rock out of the bedrock as they abraded over the surface. It'll typically happen on rocks that are a bit higher than the surrounding topography as the glacier sort of gets caught up on that edge and kind of stutters its way over the surface. It'll fracture off little chunks like that. And these crescents are actually indicative of the direction of movement of the glacier, where it sort of points down movement. So you'll essentially, this glacier was traveling in this direction in this image. And another way you can check your assumption would be to look at a compass and see what direction that kind of axis is pointing at, which should be generally trending towards the southeast. You also have glacial erratics that are left behind throughout our area. This is one of my favorite pictures. It's also one of my favorite spots. This is the glacial erratic at Rockefeller State Park Preserve. It's one of the largest in the Hudson Valley. And this gigantic stone was carried by the glaciers, probably just from the Hudson Highlands, so not extremely far. But when you think about a stone of this size, it's really mind-blowing to picture this. And actually, it probably was a lot larger when it was first broken off of its original location. The corners kind of get abraded off, and it sort of gets worn down as it kind of tumbles through that glacial movement down the valley. And so that's kind of one of the indicators. Like if you're going to go out erratic hunting while you're hiking, they'll be sort of rounded and they won't look fused to the basement rock or the surface that they're lying on top of. And of course, they'll have a different composition from the bedrock underneath them. Sometimes it's really hard to see that from the naked eye, and it might take, chemical or mineralogical testing to determine that. But others can be a little bit more obvious. So this is always a fun thing to look out for as you're hiking throughout Westchester. And another piece of evidence of these glaciers would be these massive terminal moraines, i.e. Long Island. So you'll notice there's lots going on here, a lot of different colors that indicate different rock types throughout this geologic map. But Long Island is all just one color. And that's because this area is composed of mostly glacial till and material that was essentially pushed and then left there by the glaciers. You can kind of picture the glacier like a bulldozer. And as it makes its way down the Hudson Valley, it pushes all the debris and rock and sediment and whatever it is in its path. And then it kind of just leaves all of it there once it starts to recede or melt. So what you actually see here, interestingly too, is you have two forks of Long Island, which correspond to two different moraines. So these are terminal moraine is the term you'd use for that rubble pile that builds up at the front or at that edge of the glacier. And when you have two terminal moraines like this, that's indicative of two different pulses of glaciation or of stasis of glaciers in this location. So that's an interesting fact. And this is one of the contributions. It also, glacial moraines are found on Nantucket, Cape Cod. So none of these regions really existed prior to that glaciation. So if you look back at some of the maps that I showed earlier of the kind of evolution of the continent, you're not going to see Long Island in a lot of those. And lastly, to get to our fjord question, this was also part of that glaciation process. So it's another reason why the Hudson Valley is so special. It's the southernmost fjord in North America, and it was carved by the glaciers as they descended down the valley. So glaciers carve a characteristic U shape as opposed to rivers that will carve a V shape into the sediment below or into the rock below. So we have this U-shaped glacial valley that was carved into bedrock by the glacier, and then it gets filled in by ocean water. So that's what makes it a fjord. It's not just a lake or a river, it's a fjord because it's inundated by the sea, by the ocean. And this is also why we have tides in this area. So definitely one of the things that makes the Hudson River special and just really interesting geologically speaking. So just to do a quick recap, we talked about the bedrock formation and then subsequent deformation through 4 different really significant orogenies in our area. We talked about the rifting or the breakup of Pangaea and the creation of the Newark Basin, Palisades Sill. And then lastly, to the more recent history, the glaciation that affected our area and left behind some of that evidence. So at this time, I will take some questions and wrap it up. Thanks for listening, folks.
Thanks, Kim. That was awesome. We definitely have a lot more questions. I shouldn't say a lot. We have several more questions.
Okay. I'm going to stop sharing my screen now.
Okay, including one from Pamela, but I'm probably going to mispronounce, so I'm just going to warn you. So Pamela says, hi, we live in Wells, which is part of the Mohawkian Middle Ordovician biostratigraphy of the Wells Outlier in Hamilton County. Can you speak on that?
I'm going to need to look at that written down. Can you repeat that?
Okay, it's the Mohawkian biostratigraphy of the Wells Outlier in Hamilton County. And then they said it's Middle Ordovician.
Middle Ordovician. So that's the time period.
I told you I was going to pronounce it wrong.
That's okay. I don't really know that specific unit. So I'm also not really a sedimentologist. It sounds like a sedimentary unit to me. So I'll be honest, I studied mineralogy. I studied a lot of actually planetary geology, but sedimentary geology was not really my shtick. So I don't have the great retention for like the names of the formations and their histories. If Alex Bartholomew was on the line right now, he would kill me. He was my advisor and my geology teacher in undergrad. So, but yeah, I don't know very specific information about that unit. I'm sorry. I will look into it for you. If you want to leave that comments in the chat, I'll download the transcript.
All right. Sheila says, thank you, Kim. So due to the geostructure and infrequency, New York City area is not likely to have a very big earthquake or very soon?
It's not really that likely. However, I did read somewhere that earthquakes of magnitude 6 or 7 can occur on the order of, I want to say it was like every 800 to 1,000 years in these rift valleys. And we just don't know when the last one was. So it is possible that there could be one. It would definitely be rather devastating to the area because we are not really built for that kind of shock. And we didn't really plan for that. And as far as like the development of Manhattan and the surrounding areas goes, I don't want to scare you, but I'm not going to say it's not going to happen. It just is not very likely.
Yeah, we did. Of course, when we had felt the earthquake here in Yonkers, I was in the middle of my morning at work, and so we went on a dive on the history of earthquakes in the Northeast, of course, because that's our gig. And it seems like we're far more likely to feel the aftershocks of other regional earthquakes, like in New Hampshire or Massachusetts area than we are to have our own. But
I know there was a big one in Virginia, like not too long ago that we felt up here. Yeah.
Jennifer says, I love that rock. I assume she's referring to the big one you showed earlier.
There are a lot of rocks that I have affinities for. Yeah. I love it.
Burns says, back to Palisades, that still rose as hot magma, or you said it cooled underground, so I wasn't sure how it was forced upwards.
Yeah, so Thanks for clarifying. So magma, and I don't know if I'm oversimplifying, but let me just take a step back. So magma is molten rock that's underground. Lava is rock that is extruded out onto the surface. So the Palisades Sill did form from magma that intruded from below. And this happened because as you have the removal or the kind of like that stretching or thinning of the crust as you had the extension during rifting of Pangaea, the thinner crust relieves some of the pressure from the mantle beneath it. And when you have a relief of pressure, it actually allows for melting of rock below. So that's what's called decompression melting. So rocks, it's not only temperature that contributes to their melting point, but it's also the ambient pressure. So at low enough pressure, that rock can begin to melt. And so what happens is you have the decompression melting of the rock underneath that layer that wells up to the surface. It'll find cracks or basically the separation between layers of sedimentary rock, and it will just sort of inject itself into those cracks. And so we had all of these sedimentary beds of material in the Newark Basin that were intruded by that injection. It cooled underground. And then we see it now today because it has since been sort of exhumed due to erosion.
Fascinating. So it was magma that then melted together with the other sedimentary rocks?
So in some areas, you do have contact metamorphism, which is essentially where the surrounding sedimentary rock gets sort of, I wouldn't say melted, but it gets changed chemically and mineralogically due to the heat of that magma. You have some xenoliths, which are basically little chunks or fragments of the sedimentary rock that can be found in the Palisades Sill as they sort of broke off and then were floating in this magma. But they didn't essentially mix because the sedimentary rock was already solid at that point.
Okay, cool. Thank you for clarifying.
Yeah.
Nicole says, if we want to see some other cool glacial erratics, where should we go?
So they can be found. I actually don't have a lot of great specific examples, but I would just keep an eye out for them on your hikes. Maybe there's a good resource online that would kind of outline some of these specific spots. But I have actually seen a couple at the preserve that I didn't really know about. Just like Josh has run into a couple. He'll send me a picture and I'm like, oh, that definitely looks like an erratic. So it's kind of just something to keep your eye out for. But that would be something to look into. Yeah.
It seems like the kind of thing that now that we know about it, would probably notice more.
Yeah, I know there are a couple of good examples. Like there's at least one that I know of in Central Park. And it'll be kind of obvious because it's like a big sort of rounded chunk and it's just sitting on this really smoothed over layer of bedrock. So as you could imagine, it was that glacier came by, smoothed the surface of the bedrock, and then you kind of end up with this chunk of rock left behind on top.
Cool. Going back to clay, Mark is just telling everyone if you want to see exposed clay banks, walk along the western shore of Croton Point at low tide.
Thank you, Mark.
And then Mike says, which we may have already answered this, did I hear correctly that the Palisades formed underground and were exposed by weathering? They were not an active volcanic area. I think we kind of answered that already. Okay. Lisa says, we love Kim's informative hikes at Rockefeller State Park Preserve. Can you recommend other places within an hour's drive for guided hikes?
That's a good question. Something I'm kind of actively working on with starting to plan hikes myself at some of the other parks in the region. I know me and Sarah have tossed around some ideas. I actually don't know as far as state parks lands goes. Do you have any ideas, Sarah?
Yeah, I would definitely check out the Old Croton Aqueduct. has a number of aqueduct walks. I guess they're not technically hikes because it's fairly level terrain.
Mm-hmm.
They're actually doing, if you're interested in history, they're actually doing one this Saturday, which I'm sad I cannot go to, with Shar Weigel, who is talking about some of the history along the aqueduct during the American Revolution, which sounds super cool. You could also check out our sister region across the river, the Palisades region. I don't know specifically what they have, but I know Bear Mountain State Park does a lot of programming, and they might have some guided hikes as well.
Good recommendation. Thanks, Sarah.
All right. Nicole asks, what are your thoughts on the rock slide that happened opposite Hastings on Hudson several years ago? Is that just plain old erosion or something else?
Yeah, it's funny. I was working in the city at the time, and or maybe I think it happened just before I started there. And I remember every day I'd look at it on the train, and I kind of watched it weather. You know, when it first happened, it was really bright white. You could see it was like a big scar on the sill. And then as it kind of weathered, being exposed like that, it started to darken and turn a little bit more close in color to the rest of the rock. Yeah, that's totally natural. It happens. You have those columnar joints, so you already have this kind of set of fractures throughout the rock. And then it's just naturally, it's a high point and it's exposed to wind and water at all times. So you are just going to naturally get pieces breaking off and destabilizing of that cliff face.
All right, and Mark chimed in about hikes. He says, I'm giving one Saturday morning on Croton Point with John Phillips, the Croton Point naturalist.
Oh, cool.
And then we just have lots of great thank yous and accolades for Kim on her presentation, for how friendly it is for a general audience, which I have also appreciated. And then Susan asked, what is the name of the book you planned to recommend?
Yes. Oh, I should have brought it up here. It's called The Geology of the Hudson Valley, or A Billion Years of Hudson Valley Geology. It's by Stephen Shimrich. Here, I can look it up right now, actually. And I think he just wrote it in a way that was really easy to understand, especially for the layman. Yes, it's called...
Yeah, I just pulled it up. It's called The Geology of the Hudson Valley, A Billion Years of History by Stephen Shimrich, and it was just published in 2020, it looks like, or the paperback edition maybe just came out in 2020.
Yeah, so he's a professor of geology. I think it was one of the SUNY schools. But yeah, he just has a great teaching style. I think the examples that he gives are really good analogies. So that's a really good place to start as far as Hudson Valley geology goes. And as far as people just interested in like earth science or the evolution of the planet in general, another great book for beginners would be The Story of Earth by Robert Hazen. It kind of goes into a lot of complexity. It starts off with like nucleosynthesis and stars and like where the elements come from and everything. But for those of you that like really want to dig deep into like, okay, well, where does everything come from? He also has a good way of breaking things down in a very easy way to digest.
Sorry, my lights go off if I don't move around.
You're going to have to do some jumping jacks or something.
Yeah. Oh, yeah. Charlie mentions also The Hudson Valley in the Ice Age, which is by Johanna Titus and Robert Titus. I actually went to a lecture by them a couple years ago, so that's another option if you're specifically interested in the Ice Age. So
I just bought that book recently. I haven't read it yet.
All right, that looks like that is it for questions, and it is almost 8:30, so I think we can call it an evening. Thank you so much, Kim, for joining us for tonight and taking us on that fascinating journey into this much older history than we normally talk about at Phillips Manor Hall. So it's been really neat to see how the geology has really influenced the settlement patterns and river patterns and all these great features that really shaped our history. So we really appreciate it.
It's been a pleasure. Thank you so much for having me. And thanks everyone for listening.
Yeah. Good night, everybody. Have a great night.
Good night.